Now we're going to look at some definitions. So first of all, what exactly is a confidence interval? How would we define it? A confidence interval is an interval of plausible values for a population parameter. Plausible meaning reasonable to think true. These are reasonable to think that this is true. Now, an interval, then, this confidence interval consists of two parts. A point estimate, and the ones we're going to specifically look at it are either x bar or p hat, sample statistic here, plus or minus some margin of error. Now, what exactly is the margin of error? The margin of error is how far we expect the sample statistic to vary from the population parameter at most. We set it to a certain level, we set it to a certain size depending on kind of our purposes in the estimation. Now, why do we even include a margin of error at all? Well, we include it to account for sampling variability, because we know that x bar or p hat are not going to be exactly the same as mu and p. They are going to vary somewhat. So this accounts for that sampling variability. And also to increase the chance of getting a correct estimate. There's a cartoon here that illustrates that. So here Garfield is watching the weather. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. This guy's never wrong. So if we have a big enough margin of error, we'll always be right. Obviously, in real life, we're going to want a little smaller margin of error than that. So going back to my previous screen here. Now, how do we interpret a confidence interval? Now, I want to encourage you to use the template suggested by the book, because the wording of a confidence interval is very important. It says we are 95% confident that the interval from blank to blank contains the true blank. Okay, so here's the boundaries of our interval, and this is the true population mean, population proportion, whatever it is that we're estimating. So here's an example. According to a Gallup poll published on January 9th, 2013, a 95% confidence interval for the true proportion of American adults who support the death penalty is 63% plus or minus 4%. So that is the point estimate. That's the sample proportion plus or minus the margin of error. This estimate was based on a random sample of 1,038 American adults. Interpret this interval in context. So first of all, before we interpret, and I know you're probably reading this at this point, but let's think about, here's the confidence interval. 63 minus 4% and 63 plus 4%. So that's what the confidence interval looks like. I want to mention that there are some conditions that have to be met. First of all, is this a random sample? And it says yes. Let's see. A random sample of 1,038 American adults. The 1,038 is still less than 10% of the population of all American adults, and so we can, this validates the 10% condition that says we consider these results independent, even though we're sampling without replacement. Also, remember that in order to use the sampling distribution of sample proportions and have it be a normal model, we have to have NP and NQ both greater than 10. Well, N is the sample size, 1,038, and P, well, we don't know P, but we know P hat here would be 63%. So we have 63% of 1,038 and 37% of 1,038, both of which are far larger than 10. So all of our conditions are satisfied to actually form a confidence interval. So how do we interpret this in the context of the problem? We are 95% confident that the interval from 59 to 67% contains the true population proportion of American adults who support the death penalty. Okay, that is a very good statement of what the confidence interval is. Now I want to point out some of this language. We're confident that our interval contains the true population proportion. We don't say that 95% of the time the population proportion will be in that interval, because that implies that the population proportion is sometimes in that interval and it's sometimes not. No, the population proportion, the population parameter, the population proportion in this case, never changes. It stays the same. It does not move. What changes are the different intervals that we would get from different samples. So we say this particular interval, we are 95% confident that this particular interval captures that population proportion, the true population proportion, but so we can think of the interval moving around but not the actual population proportion. Now, how do we interpret a confidence level? In other words, what does it mean to be 95% confident? To investigate this, we are going to look at an applet. Okay, I'm going to go ahead and go to the applet and just show you this. So here we have a confidence level of 95%, a sample size of 20. I'm going to take one sample, and you see the dots represent the values in the sample, and there are 20 values. The black circle here, the black dot, represents the sample mean, the mean of all of these little gold dots. And then the two little segments sticking out represent adding about 2 standard deviations of our sampling distribution to each side of the sample mean to form a confidence interval. And we notice that that confidence interval contains the true population mean, which is indicated by this green line where mu is. So let's do a few more samples. Let's do 25 samples. Now notice every one of those samples, they kind of vary because the sample mean varies, but every one of our intervals contains the true population proportion. Let's do another 25. Oh, there's one that missed. So we got a particular sample proportion that was unusually low. If we look up here, this would be the distribution of sample means, and so that is unusually low to have one way over there. And it misses the true population proportion, or true population mean. So let's do some more. This time we have another miss, another miss. This time there's a couple misses. Notice if we kept going quite a long time, we would notice that the overall percentage of these intervals that hit or contain the true population proportion should pretty well be close to 95%. Okay, so we're doing lots and lots of those. So if we go back to our notes here, what does it mean to be 95% confident? 95% confidence means that if I take many, many samples of the same size from the same population and make confidence intervals, I expect about 95% of them to contain the true population mean. So that's what it means to be 95% confident. Now let's go back to our applet that we were using and do some other things. Let's say what happens if we were to change the confidence level. So I am going to make the confidence level lower. What do we notice here about the size of the intervals? Notice they're getting narrower, and because they're getting narrower now, more of them are not containing the true population proportion. If I make it even more confident, notice that more of them, I've got 99% of them in my percent hit. If I increase my samples a little bit, okay, I'm 98% confident, and I have 98% that hit the true population proportion like I expect. So it turns out that if I were to lower the confidence level, I am going to have less confidence that my interval actually contains the true population mean. But notice that the less variability in my interval. So basically, this is a more precise estimate, less variability. I'm farther from, if I happen to get the true mean, I'm farther from being wrong, but I'm wrong more often. So let's go back and summarize this on the next page of our notes. Oops, I didn't really want that to be here. Okay. Well, that's all right. An increased confidence comes with an increased margin of error. We notice that. I'm going to kind of cover this up here. Increased confidence comes with an increased margin of error. So in other words, if I have a higher level of confidence, I'm going to have a larger margin of error, and because of that larger margin of error, I'm more likely to capture the true population mean. An increased precision on our estimate, in other words, a smaller margin of error, comes with a decreased level of confidence. I have less confidence in my estimate because I'm more likely to miss the true population mean. So, how can we reduce the margin of error without decreasing our level of confidence? So let's go back to this here, and notice I'm going to go back to 95. And let's see what happens when we change the sample size. So let me first sample at 25 so you can kind of see what they look like. So notice what the intervals look like. And if I kept sampling more and more, I'm going to get close to that 95% hit rate. In other words, I'm only going to miss containing the true population mean about 5% of the time. But what happens if I make the sample size 40 instead of 20? Notice my percent hit is still around 95%. So my level of confidence stays the same. I'm 95% confident, but notice that the degree of precision in my estimate is now greater because I have smaller intervals. So when I increased the sample size, it made my intervals smaller. Now I don't know if this will change dynamically as I increase. Now I think I have to reset. So let's make these even bigger. Let's make the sample size 150 at 95% confident. Oh my gosh, look how, notice that my hit rate is still the same, but my precision of my estimate is astronomically good now with this large sample size. So 150 gives me excellent results. Not only a high level of containing not only the 95% confident that I'll get the true population mean, but also very little variation in my estimate. So going back to our notes again, how can we reduce margin of error? Increase the sample size. Okay, so I think I'm going to switch to another page here for a minute. Okay, so this is what we have so far. Now let's talk about the general formula for a confidence interval. The general formula for a confidence interval is the point estimate, and that, remember, comes from the sample, like a sample mean or a sample proportion, plus or minus a margin of error. Now, let's go ahead and put down here that the points estimate is a sample statistic. So I take a sample, I calculate the statistic for the sample, and that's my best guess for the population mean or the population proportion. I'm using X bar or P hat to make a guess about mu or P. Now, where does the margin of error come? The margin of error comes from two parts. There is a critical value, and I'll explain what that means in a minute, times the standard deviation of the statistic. So both of those put together form the margin of error. So this together is the margin of error. Okay, is that together. Now, let's think about, first of all, the standard deviation of the statistic. We noticed that as we increased the sample size, we could reduce the margin of error. Why does that work? Why does increasing the sample size reduce the margin of error? So remember, the sample size is denoted by n. So as n increases, let's think about the margin of error. Remember that sigma of x bar is sigma divided by the square root of n. And remember that sigma of p hat, the standard deviation of sampled proportions, is the square root of pq over n. So notice, as n increases, that means the denominator is getting bigger, which means the standard deviation is getting smaller. So that makes very good sense why that works. Now, what about the critical value? So I'm going to write here that this depends on sample size. So if this part depends on sample size, that explains why sample size affects the size of the interval and the margin of error. Now, the critical value depends on the confidence level. For example, if we have a 95% confidence level, basically we're adding about 2 standard deviations on either side of our sample statistic. So this critical value is actually the number of standard deviations that we add for the margin of error. So we have the size of the standard deviation, and then how many standard deviations that we add, and put those two together becomes the margin of error. Now, last little bit just to show you is just a couple of important reminders. What is important to remember when constructing and interpreting confidence intervals? I want to give you just kind of a real life, like if you're looking at confidence intervals in real life and you see maybe a poll in the newspaper and it has, saying support for this candidate is about 45% with a 3% margin of error. Realize that the methods that are in this class are very basic. This is an introductory level course, so we don't go into all the details and the nuances and different things that could happen. All of our methods are assuming that we have a simple random sample. In real life, there isn't always a simple random sample. Sometimes we do stratified or cluster samples or different things like that. So if we don't have a simple random sample or a random assignment in an experiment, then these methods actually aren't totally accurate. But they're reasonable for an introductory level course to study. We have to start out basic and then build up. The margin of error in a confidence interval also accounts for sampling variability, but not for other sources of variation or potential bias in the data. So, for example, if you're doing a survey, you might have undercoverage or non-response involved and have some bias, and so your data has some variability that is outside just the variability due to sampling, and so once again your interval may not be as accurate as it seems just because of the way the sample was taken, for example. So in real life, we do have to remember there is more to statistics than just what we're studying in this class. But for our purposes, we're just going to make some assumptions that things are as they are supposed to be for our methods. When you get to the next video then, we are going to look at a practice problem for what we've done so far, and then we'll move on to section 8.2 in the video after that.